Hello all. Welcome to this course, Thermal Management of Electronic Devices. So in this particular lecture, we'll be discussing about the following topics. We'll introduce the term heat. Then we will discuss about thermodynamics versus heat transfer. Then we define the subject called heat transfer. Then we will discuss about modes of heat transfer. Okay. So how do you define the term heat? So heat is a form of energy. Form of energy can be transferred from one system to other as a result of temperature difference. This is defined as heat. Already we got introduction to the term heat in thermodynamics. Now, why do we need to have a separate subject called as heat transfer, a topic called as heat transfer? Let us discuss this with the help of an example of a thermos flask. Let us consider a thermos flask. We know thermos flasks are used for storing things hot or things cool even. So let us erase this. I take an eraser and I try to erase this. So I think, so let's take an example of thermos flask. So we know it is used for keeping things hot or cool. So assume that a coffee is kept inside thermos flask at 90 degrees C. So what thermodynamics can do? So thermodynamics can tell us if the coffee in the flask goes from 90 degrees C to 70 degrees C, how much will be the heat transfer? It will talk about how much will be the heat transfer. If you assume that there is coffee in the flask, it will tell how much will be the heat transfer. It speaks about only the amount of heat transfer. But those who are interested to buy thermos flask will worry about the time taken for the coffee to go from 90 degrees to 70 degrees C. As an engineer, we also design based on this only. So we will be worrying about time taken for the coffee to go from 90 degrees C to 70 degrees C. This is what we will be worrying about. So thermodynamics cannot give this answer, for which require a subject called as heat transfer. So in addition to thermodynamics basic laws, so here also we require thermodynamics. In addition to thermodynamics, we need new formulas to determine the time taken. In other words, we can say we need thermodynamics, we need heat transfer. In addition to thermodynamics, we need heat transfer. So in simple words, we can say thermodynamics deals with systems that is in equilibrium. Those are in equilibrium. But heat transfer, and this thermodynamics can give only the details of amount of heat transfer. Amount of heat transfer. But subject heat transfer can give the details of rate of heat transfer, time taken for heating or cooling, time taken for heat transfer, that is heating or cooling, and temperature variation. These are the topics of the subject called heat transfer, which thermodynamics cannot help. So it is very clear why heat transfer is required. Now we'll get into the topic of modes of heat transfer. Let us discuss about various modes of heat transfer. Modes of heat transfer. So let us recollect few points. We know heat is a form of energy which can be transferred from one system to the other as a result of temperature difference, and heat always flows from high temperature to low temperature. That also we know. High temperature to low temperature. So there are three modes of heat transfer. One is conduction heat transfer. The second one is convection heat transfer. And third is radiation heat transfer. Let us discuss one by one. First, let us consider the mode conduction heat transfer. So conduction can occur in solids, liquids, and gases. So how can we define this? The heat is transferred from high energetic particles to adjacent less energetic particles. This is how conduction is defined. How do they occur in solids? In solids, they occur by two reasons. One is free electron movement, free electron flow, and second is lattice vibration. These two reasons are allowing the conduction to happen in solids: free electron flow and lattice vibration. So the lattice vibration is also called as phonon. In liquids and gases, conduction occurs because of diffusion and collision. So this can be commonly called as fluids. Now let us discuss the governing equation for conduction heat transfer. The law which governs conduction heat transfer is called as Fourier law of heat conduction. Fourier law of heat conduction. So consider a rectangular block like this. So consider a rectangular block of some material. Let this thickness be L. I'll draw it neatly. Let this thickness be L thickness, and let this area be area normal to heat flow. Let's assume that, so we have I draw it neatly. So we have two surfaces, these two rectangular surfaces. Let's consider this. Let this surface be at temperature T1. Let this surface be at temperature T1, and let this surface be at temperature T2. I mean, this is the surface one which has got T1, and this surface got T2. Let us assume that T1 is greater than T2. T1 is greater than T2. And this area is AN, area normal to the heat flow, and this area is also AN. So AN is called as area normal to the heat flow. So it was found that this conduction heat transfer rate of conduction heat transfer, I mentioned it is Q conduction, is directly proportional to the temperature difference T1 minus T2, which means when temperature difference is doubled, the conduction heat transfer has doubled, and directly proportional to the area normal to the heat flow. That is important. It is not simply area, it is area normal. We assume that it is happening in this direction. Heat transfer occurring normal to this rectangular face. So therefore, it is directly proportional to area normal to the heat flow, and inversely proportional to the thickness across which the heat is being transferred. So L is thickness across which conduction heat transfer is occurring. Conduction heat transfer is occurring. Heat transfer is happening. So this is the formula. Conduction heat transfer is directly proportional to the temperature difference, directly proportional to the area normal to the heat flow, and inversely proportional to the thickness across which the conduction is occurring. So the proportionality constant we can remove. So I repeat the equation. Q is directly proportional to Q conduction is directly proportional to area normal to the heat flow, temperature difference, and inversely proportional to L. And this proportionality constant is called as K. K into AN into T1 minus T2. T1 minus T2 by L. So when the thickness is very smaller, this can be written as Kan into dt by dx. And this is called as Fourier law of heat conduction. A minus sign will be included here. We know actually we have to put final temperature minus initial temperature, T2 minus T1 here. It is T2 minus T1. Correct in the previous slide also. So this should be T2 minus T1. The customary way is doing is final temperature minus initial temperature. So it is An into T2 minus T1 by L. So therefore the T2 minus T1 will have a minus sign. So we know that it will have a minus sign. I write it neatly. So this why do we put T2 minus T1? Because we used to write like that, final temperature minus initial temperature. So when you put like this whole term will say, for example, T1 is 100 degrees C and T2 is 50 degrees C. 50 minus 100 will get a number called as minus 50. To make the whole thing positive, we add a negative sign here. And this equation is called as Fourier law of heat conduction. Fourier law of heat conduction. Now we have to discuss about the units of this. Shall we discuss the units of this? Yes. We'll do it in the next video.